Certainly I'm a little bit strange, but sometimes I try to imagine what it would be like to solve the entire power system for even a small village. Without even factoring in the human element that is always turning things on and turning things off, the problem becomes overwhelming. There are so many different types of things that can be connected to the power line. A hairdryer, a refrigerator, a light, and an electric blower are dramatically different AC loads. And then there are all of the things that take AC and convert it to DC before the electricity is used. In addition, each of the houses on the block is different and turns these or other things on at different times. Some of the neighbors might be charging electric cars, or some have workshops in their basement or garage, and there are hundreds of these homes. And what if we start to consider some of the businesses or industrial facilities in the village? They might have large refrigeration systems or industrial-sized electric loads. The whole thing becomes an overwhelming mess. Alright, so the introduction serves as another argument for simplification and modeling, but the central issue in this video is AC power. We saw last time that a largely inductive load can result in a power that has a larger imaginary component than a real component. Since many of the things that consume large amounts of electricity involve electric motors, and motors are largely inductive loads, any issues that arise due to this are going to have an impact on how we deal with the power supplied to them. If the power company charge is largely based upon the real power consumed, is it free to run electric motors? And if the power company sizes the power lines based on the handling of the current represented by the real power, will those lines be enough? If a manufacturing company with a large inductive load draws power from the same line as your home, will that affect things in your house? Hopefully, by the end of this video, you'll have an idea how to answer these questions. We are going to begin today with a time domain circuit, and we will determine the power delivered to the load. This will allow us to practice some of our analysis skills on the way to learning more about complex power. Here we have a time domain circuit that is separated by a pair of terminals into a source circuit on the left and a load circuit on the right. In this case, I would like to determine the power that is delivered to the load. Since we have a sinusoidal source and I want to discuss complex power, let us take the circuit to the phasor domain. Beginning with the source and putting the angular frequency to the side, the source has an amplitude of 100 volts with a phase angle of 0. The top inductor is converted to the phasor domain by multiplying J times the angular frequency times the inductance, resulting in an impedance of J 3.77 ohms. The 30 microfarad capacitor is converted to an impedance by taking 1 over the imaginary number times the angular frequency times the capacitance, resulting in a negative J 88.4 ohms. The inductor on the right hand is again J times the angular frequency times the inductance, resulting in an impedance of J times 75.4 ohms. With the circuit now in the phasor domain, we can then decide how to analyze it. When I first looked at the circuit, I split it into a source and a load, and I think it would be helpful to continue the analysis along that vein. We can find the Thevenin equivalent circuit of the source and then connect that to the load. Since the circuit contains only an independent voltage source, the equivalent impedance can be found by turning the AC source off. A short circuit guarantees 0 volts, and combining the impedances. The 500 ohm resistance and the minus J 88.4 ohm impedance are in parallel. Impedances are combined just like resistors, so the reciprocal of the impedance is the sum of admittances. This results in an impedance of 15.16 minus J 85.74 ohms, which is then in series with the J 3.77 ohm impedance. So the total equivalent impedance is 15.16 minus J 81.97 ohms. To finish determining the equivalent circuit, we need to determine the open circuit voltage. In this case, since no current will go through the inductor as it is in series with an open circuit, the open circuit voltage will also be across the capacitor. Determining the open circuit voltage is then as simple as doing voltage division between the capacitor and the resistor. This results in an open circuit voltage of 17.41 e to the minus J 79.97 degrees volts. So now we have the Thevenin equivalent of the source. If we reattach the load, we can combine the parallel impedances of the resistor and inductor. We combine the parallel impedances by adding the reciprocals, resulting in an impedance of 24.89 plus J 66.02 ohms. Now our circuit consists of a voltage source with 2 series impedances. We are trying to determine the complex power delivered to the load, so we need to know the voltage across the load and the current through the load. The load voltage can be found by doing voltage division. We find that the voltage is 28.5 e to the J 11.09 degrees volts. An interesting thing has occurred here in that the magnitude of the load load voltage is higher than the equivalent source voltage. If this troubles you, you should determine the voltage across the source impedance and then do a KVL loop to verify the voltages add to 0. If this does not trouble you, you probably need to perform the KVL calculation. Either you are not troubled because you understand resonance, which we have not talked about, or you have missed something fundamental along the way. When energy storage devices are involved in a circuit, it is possible that the energy exchange between the devices, like capacitors and inductors, can result in the magnitude of individual voltages being higher than the source. Kirchhoff's voltage law will always be true, however, so all of the voltages in any loop will still add to 0. Back to the power calculation. We still need to determine the current through the load. Though this can be determined in more than one way at this point, I am choosing to determine the current by dividing the source voltage by the total impedance of the circuit. This results in a current of 403.94 e to the minus j 58.25 degrees milliamps. With the load voltage and current both determined, we can calculate the complex power by multiplying the RMS load voltage times the complex conjugate of the RMS load current. This will be the same as multiplying the product of the phasor voltage and the conjugate of the phasor current by 1/2. The result is a power of 5.76 e to the j 69.34 degrees voltamps, or in rectangular form, 2.03 plus j times 5.39 voltamps. We have the complex power delivered to the load. Now we need to develop some vocabulary around this concept so we can begin to interpret what we have computed. Though the magnitude of the complex power is 5.76 voltamps, we see the average power is only 2.03 watts. That has to do with the phase angle difference between the load voltage and the load current. We have a rather straightforward way of handling this. The magnitude of the complex power is called the apparent power. Apparent power is the product of the RMS voltage and the RMS current. Apparent power does not indicate the amount of power being dissipated by something, as it may be entirely reactive, and therefore no power will be dissipated, but it does give an indicator of the magnitudes of the voltages and currents. Since in many power systems the voltage is known, apparent power can indicate how much current carrying capability is necessary for the system. Apparent power does not have any indication of the relative phase of the voltage and current. To deal with that, we have a quantity called the power factor. The power factor is the cosine of the difference in phase between the voltage and current waveforms, and therefore can have any values between and including -1 and +1. Values of plus or -1 indicate that the power is entirely real, while a value of 0 indicates that the power is entirely reactive. It should be noted that for anything that uses power, the power factor will always be positive. Also, since the cosine is an even function, we cannot tell if the reactive power is negative or positive from the power factor. If the reactive power is negative, we add the term leading to the power factor. This occurs for loads that have a capacitive reactive component. In this case, the current will lead the voltage. If the reactive power is positive, we use the term lagging power factor. This occurs when the current lags the voltage and indicates an inductive load. To help remember this, the mnemonic Eli the Iceman can help. E is the electromotive force, or the voltage, L indicates the inductor, and C indicates a capacitor. In ice, I, current, is before E, voltage, so the current leads the voltage in a capacitor. Both the apparent power and the power factor are very important to electric companies. Maybe the simplest breakdown is that the power company has to supply enough power to cover the apparent power, but can only charge for the real power used. The electric company is very aware of this, so it will keep track of both the apparent and the real power that a consumer is demanding. If the ratio of the real power to the apparent power, this is another way to think about the power factor, is too small, the electric company will charge a higher rate for the electricity for that customer. The higher rates are often considerably higher, so there is some incentive for the company to increase their power factor if at all possible. The question then becomes, how can an electric customer modify the power factor? An electric motor will always look like an inductor, and if most of the things that are drawing power are inductors, are we locked in? To answer that, we can look at complex power from a different angle. Let me introduce you to the power triangle. The magnitude of the complex power is simply the polar equivalent of the rectangular complex number with the real coefficient of the real power and an imaginary component of the reactive power. The power factor is the cosine of the difference in the phase between the voltage and the current, which is the angle adjacent to the real power. It is also clear from our knowledge of trigonometry that the power factor is also the ratio of the real to apparent power. If we add to the load a component that has a leading power factor, the overall reactive power will be reduced, which in turn will increase the power factor. So if we have a situation where there's a load that results in a lagging power factor, this would be an inductive load. We could put a component with a leading power factor, that is a capacitor, in parallel with the existing load, and the overall reactive power will be reduced. To illustrate this, we can look at a simple complex power problem. Here we have a resistive and an inductive load connected to a 480 volt RMS source. To determine the power supplied to the load, we will need to determine the current through the load. That is calculated using Ohm's law. If we convert the 100 plus J 400 ohm impedance to polar form and divide the input voltage by the impedance, we get a 1.164 amps RMS current with a phase angle of negative 75.96 degrees. Voltage and current are RMS values, so if we multiply the voltage times the complex conjugate of the current, we will get the complex power. The power factor is the cosine of the difference in phase between the voltage and current, which will be the same as the angle of the polar expression of the complex power, in this case 75.96 degrees. This results in a very small power factor of 0.243 lagging. Remember that it's necessary to specify lagging or leading for the power factor, as that information is lost in the cosine. For our first attempt at power factor correction, we will try to eliminate the power factor entirely by placing a capacitor in parallel with the load. If we look at the complex power, we see that the reactive power we are trying to counteract is a positive 542.12 volt amps reactive. We need to determine the power that needs to be exchanged with the capacitor. This will allow us to determine the current through the capacitor, which will allow us to determine the impedance of the capacitor, which allows us to calculate the actual value of the capacitance needed. The power exchanged with the capacitor will be entirely reactive, as the impedance is entirely imaginary. So to determine the power exchanged with the capacitor, we simply put a negative sign in front of the power of the load. We can solve the equation for the complex conjugate of the current and take the conjugate of the result to find that the current through the capacitor is 1.129 amps RMS with a 90-degree phase angle. We can then determine the impedance of the capacitor by taking the ratio of the RMS voltage and the RMS current. It is important that both of these quantities are in RMS. With an impedance of minus J times 425 ohms determined, if we get a positive impedance for a capacitor, we made an error somewhere. We can equate that to 1 over J omega C. Omega is given as 2 pi 60 radians per second, so we get 6.24 microfarads for the required capacitor. I think we should take a couple quick looks at some practical aspects of this problem. First, let us see what the capacitor did to the RMS current from the source. We know that the source current must be equal to the capacitor current plus the load current. Both the capacitor and the load have the source voltage across them, so we can solve for each current using Ohm's law. The load current remains the same as before and is 0.282 minus J 1.13 amps RMS. The current through the capacitor ends up being positive J 1.13 amps RMS. The sum of the currents is entirely real with the value of 2.82 amps RMS. As we might expect, in order to have no reactive power, the current must be in phase with the voltage. Now a few practical considerations regarding the capacitor. We calculated a capacitor of 6.24 microfarads. That is not a value of capacitor we can purchase, making it impractical. Any value that is not 6.24 microfarads will result in some reactive power. Capacitors that are in this range, by the way, generally have tolerances of plus or minus 20%, so it really does not matter if we get the correct nominal value. We also have to consider the voltage rating of the capacitor. If the source is 480 volts RMS, that means the capacitor needs to be able to withstand that voltage. Also remember that the peak voltage is closer to 680 volts. An important practice when sizing components is called derating. If we derate a capacitor at 50%, which is a good practice, that means we need to use a capacitor that can handle twice the voltage we think it is normally going to encounter. There are several reasons for this. An obvious one is that the component has a tolerance. Expecting exact values for voltages and currents is not reasonable. Another is that running a component at the maximum rating is more stressful to the component, and the component is more likely to fail. Just like a glass of water that is filled to its absolute capacity is more likely to spill. Another consideration is that every system encounters some unexpected voltages from time to time. Whether this is a transient at startup or a voltage spike from an external source, you get the idea. We need some wiggle room for circuit reliability. In this case, we now need a capacitor that is about 6.2 microfarads that can handle 960 volts RMS or 1360 volts peak. Take a couple of minutes to find such a capacitor. If you find it, look at the price. We probably want a better solution. I would love to point you towards that solution, but I think we'll have to wait for the next video. In this video, we found the equivalent circuit of a source and load in the phasor domain. We then determined the complex power delivered to the load. We then looked at the concept of apparent power and the power factor. After a brief look as to why the power factor is an important concept, we went on to determine how to change the power factor to 1 for a circuit. Next time we'll talk about correcting a power factor to a specified level. Until then, go out and make it a great one.